Hello, welcome to another module in this massive open online course. So we had in the past module, we have started our discussion regarding stochastic processes. So let us continue our discussions regarding stochastic process, right. So we were talking about the one step transition probability. So we were talking about the one step transition probability, that is the probability that xn plus 1 equal to Sj given xn equal to x Si, this is equal to the probability that x1 equals Sj given x0 equals Si, and this is essentially does not depend on n, it is time homogeneous, right. We call this essentially as something that is time homogeneous. And this quantity is denoted by Pij. We are denoting this transition probability by Pij, and this is essentially what we term as the one step transition probability. Remember, this is what we are calling as the one step this is what we are terming the one step transition probability. Okay. And now, out of these one step transition probabilities, one can create this transition, what is known as this transition probability matrix. So, I am going to have an n cross n matrix n cross n matrix P such that the ijth element of P is basically Pij, and I can formulate therefore, which is again remember the probability xn plus 1 equals Sj given xn is Si, and therefore, I can form this matrix P as I can form this matrix P with the elements P11, P12, so on P1n, P21, P22, P2n, Pn1, so on up to Pnn. So, this is naturally the n cross n matrix corresponds to the one step transition probability. So, this is simply known as the transition probability matrix. This is simply termed as the transition this is termed as the transition probability matrix, which essentially fully characterizes your discrete time Markov chain. That is the important. So, you have the one step transition probabilities, and from the Markov property that is essential to characterize the evolution of the stochastic process. So, this essentially characterizes, you can clearly see this characterizes the DTMC. its evolution and behavior, and this can tell us about many properties of the DTMC that we are going to keep inferring. Okay. Now, now here you can see, for instance, now you can see P2, let us look at some of these elements. For instance, let us say, let us ask this question, what is P21? P21 equals the probability of transition from state 1 to state 2, that is probability xn plus 1 equal to 2 given xn equals 1. I am sorry, probability xn plus 1 equals 1, sorry, this is the probability transitions from state 2 state 1, that is Pij, this is probability xn plus 1 equal to 1 given xn equals 2. Okay. So, therefore, if you look at the rows correspond to the starting states, right. So, if you look at the rows correspond to the starting states, that is the xn, right. Rows correspond to the starting states, and if you look at the columns corresponding to the ending states in the transition. Columns correspond to the ending states. So, rows correspond to the starting states, columns correspond to the ending states in the transition. Okay. And this is essentially your n cross n transition probability matrix, which Pij denotes the probability of transition from Pij denotes the probability of transition from state I to state j. There is a probability that xn plus 1 equals Sj given xn equals state I. Okay. And note that also this is important, and it is straightforward to see that, not difficult to see. Note that if you look at the summation over all j, that is j equal to 1 to n, if you look at all these conditional probabilities, xn plus 1 equal to Sj given xn equals Si, this must be equal to 1. That is, starting in state Si, if you look at all the conditional probability, sum of the probabilities of transitions to all the other states, that must be equal to 1. And therefore, this implies the sum of the probabilities in each row must be equal to 1. This essentially implies sum of all entries in each row of P this implies that if you look at summation j equal to 1 to n Pij, this must be equal to 1 for all I, for each I, that is 1 less than or equal to I less than or equal to n. That is, if I take any particular I and take the sum of Pij over all j, that must be equal to 1. That is the sum of the transition probabilities, all the transition probabilities starting from the state I. Okay. And further, it goes without saying, because each of these is a probability, it naturally follows that Pij has to be greater than or equal to 0, cannot be negative. It can be 0, probability can be 0, but cannot be negative, each, since each is a probability. Okay. Since each is a probability. Okay. Let us take a simple example. Let us take the probability matrix P equal to 0.35. Let us take a n equal to 3 case discrete time Markov chain, that is your P is of size 3 cross 3. We can have a probability transition matrix that looks like this: 0.35, 0.35, 0.3, 0.2, 0.7, 0.1, 0.4, 0, 0.6. You can see sum of elements in each row equals 1. For instance, let us take a look at this element P23. What is this? This is your P23. This is the probability xn plus 1 equals 3 given xn equals 2. That is, starting from the state 2, what is the probability that the next state is 3? There is a 0.1 probability that the next state is 3. Now, this 0 shows something interesting. 0 shows that starting from state, if the state xn equal to st, probability xn plus 1 equals 2 given, or xn plus 1 equals, I have to say xn plus 1 equals, sorry, S3 S2, xn plus 1 equals S3 or xn plus 1 equals S2 given xn equal to S3, this probability is equal to 0. And similarly, let me just try to see if I have, so this is the probability of transition of state 2 to state 1. So, I have to write xn plus 1 equals S1 given xn equals S2, so on. Okay. And therefore, now we can write the state transition diagram. Now, we can also represent this transition probability matrix as a state transition diagram. We can draw each state and represent these transition probabilities on arrows. Okay. So, that is another way to represent a DTMC, although a slightly more elaborate, it is more visual, right. The matrix representation is more compact and suitable for mathematical manipulations. The pictorial representation, the figure that we are going to draw, is better, it is easier to visualize. So, it is a visualization tool. Okay. So, one can draw the state transition diagram for this DTMC. So, the state transition diagram so you have .35, right, the probability, this is basically your P11 transitions from 1 to 1, state 1 to 1, you can call this as S1, S2, S3, S1 to S2, this is P12 which is equal to 0.35, S1 to S3, this is P13, this is equal to 0.3. Now, S2 to S1, this is 0.2, this is P21, I believe this is 0.2, S2 to S2 that is P22, this is 0.7, and finally S2 to S3 this is P23, this is 0.1, S3 to S1 this is essentially this is 0.4, S3 to 2, remember the probability is 0. So, there is no branch, which shows that it cannot transition from state 3 to state 2 because the probability is 0. The only remaining one is transition from 3 to 3 and that probability is 0.6, and this is essentially your state transition diagram. So, this is the state transition diagram for the DTMC. This is something that is very convenient. I would like to say this is that this is convenient for visualizing. Something that is very convenient for visualization. Okay. All right. So, this basically is the state transition diagram. Let us try to look at a simple example application of this discrete time Markov chain. For instance, let us consider an example in the context of industrial reliability. Let us assume that there is a machine. The machine can be in one of two states, that is it can be in an operating condition, that is it can be operational, or it can be broken, it is faulty, and it can transition between these states. Now, let us try to build a model for this. So, let us try to look at a more, I would say, a practical example. So, we have industrial reliability. Let us talk about industrial Now, what happens with industrial reliability? So, let us say we have a machine and this can be in two states, S0 equals, or we can say S1 equals operational, S2 equal to faulty, that it is not operational. Okay. Now, let us try to build a model, and it can transition between these two states, right, from operational can turn to faulty, it can be broken, and then from faulty it can be repaired and become operational once again, and then one can build a model for this. Now, of course, practically one would hope that the machine does not break down too often, right, and the probabilities will reflect that. All right. Okay. So, xn we know now there are two states. So, each time instant Sn can belong to one of these two states, that is S1 or S2. Now, we need the transition probability. So, this is essentially your state space. You might well remember this is your state space, and the probability. Now, let us look at the transition, the one step transition probabilities. Now, to characterize this, we need to give the one step transition transition probabilities. Probability xn plus 1 equal to S1 given xn equal to S1, that is it goes from a working state, an operational state, to operational, that is it is originally operational S1, goes into the operational state in the next hour. Let us say this n, each time instant is an hour, right, first hour, second hour and so on, hourly, that is its plant is, or the industry is running, the plant is running continuously, and we are monitoring the status of this machine. Okay. So, it goes from operational to operational, operational in 1 hour to operational in the next hour. Probability of that is 0.95, which shows that it is a fairly reliable machine, might not be extremely reliable, but fairly reliable. Similarly, now let us characterize the probability of breakdown, that is probability of xn plus 1 equal to S2 given xn equals S1, that is operational, that is it is going to a faulty state from one that is originally operational, that is. Now, remember we take the all the probabilities corresponding to each state Si, S1 initial state, then they should add up to 1. So, naturally probability of xn equal to S1 given xn plus 1 equal to S1, that is P11 equals 0.95. So, that automatically means that P12, right, it goes from operational to faulty, that must be equal to 1 minus 0.95, that is 0.05. So, this must be equal to 0.05, that is 1 minus 0.95, and further this is your basically P11, this is your P12, and this essentially is what we are calling as the breakdown probability, right, working to operational to faulty. This is essentially your breakdown probability. This is the probability of breakdown. Now, let us look at probability xn plus 1 equals S2 given xn equals S2, that is P22, that is it goes from faulty. So, it is faulty at the beginning of the hour and it continues to be faulty, that there is no repair, there is certain probability with which it cannot be repaired, and in that hour, and that probability is basically let us say that probability is 0.10, and therefore, P21, the probability of it being repaired in that hour after, in an hour after breakdown, is probability xn plus 1 equal to S1 given xn equal to S2, that is equal to 1 minus 0.10 equal to 0.90, and this is the probability of repair, right. So, it goes from faulty to operational, and this is essentially the probability of repair, right. This is essentially the probability of repair, and now we have all these quantities, that is each Pii, right. We have the Pij's, each Pij is greater than or equal to 0, summation of Pij over all j is equal to 1. Now, we write the one step transition probability matrix or simply the transition probability matrix, and therefore, now the P, which is the transition probability matrix, remember there is 2 states. So, this is going to be a 2 cross 2 matrix, this is going to be 0.95, 0.05, 0.90, 0.10. This is your transition probability matrix. This is the transition probability matrix, okay, that is basically built for, and now you can see the rows correspond to initial state, column corresponds to the final state, and sum of each row is equal to 1. Sum of the probabilities, transition probabilities, for instance, this is your P11, this is your P12, this is your P22 and this is your P21, and you can see sum over each row equals unity. All right. So, this is the transition probability matrix for this problem. All right. So, with this let us stop this module here, and we will consider other similar examples and continue to build on this these concepts, especially pertaining to the analysis of the discrete time Markov chain in the subsequent modules. Thank you very much.